Assalamualaikum and good day to everyone. Now we are going to study on concrete testing part 1 about concrete mix design. So the aims of the lecture today is to provide mix design based on the concrete mix design requirement. So the expected outcome at the end of this lecture, you should be able to produce good grade of concrete. Why we need to do the concrete mix design? Because it is to determine the relative proportions of the ingredients of the concrete to achieve the desired properties in the most economical method. Here is the content for the lab report. So the first is the cover page. So this is the examples of the cover page for the engineering laboratory. So the experiment title is the concrete laboratory. So here, this is the subject code, subject course name, and the experimental title now is concrete mix design, and you need to include what is the date of experiment and your group number, sections, the group members and ID numbers here, and the person in charge, and then remark and endorsement that you have submitted the lab report. So at the end of the testing, you need to produce a technical report. And then this is the content. So here, this table of content consists of introduction, objective, apparatus, procedure, result, discussion, conclusion, and you need to include the reference and appendix about the experimental title. Next is introduction. Why we need to do the concrete testing? Here, a good concrete mix design creates the successful construction. How? Here, it means that the quality of concrete must meet the highest quality performance. And then, concrete mix design involves a process of preparation in which a mix of ingredients creates the required strength and durability for the concrete structure. So, because every ingredient in the mix consists of different properties, it's not an easy task to create a great concrete mix. It is imperative that all ingredients be tested to determine their physical properties and the bearing capacity of the project location. So what is the ingredients? Here, the ingredients to be tested is water, fine aggregate, coarse aggregate, cement, chemical, reinforcement, and soil. And also, why we need the values? So the values of the physical properties obtained after testing will be used as the basic for all concrete mix design consideration. And then this will ensure the structure will be sound and prevent failure of the mix. It is important to note that the ingredients for the mix might vary from one project location to another. So, the physical properties must be tested for the requirements specified for each location. So, that is why we need to do the concrete testing. For example, before we do the concrete testing, we need to test all the ingredients. For example, sieving analysis for fine and coarse aggregate. Next, the following is the factors affecting the concrete mix design. So here, what is the factors that affect for the strength and durability of the concrete mix design? So here, number 1, we have grade designation. So here, concrete strength is measured in Newton per millimeter squared when subject to test after curing in any curing medium. The choice of concrete grade depends on its usage. So we have various of grade depends on the condition where you want to apply. For example, for the beam, for the roof beam, for the concrete beams, for the column, for the foundation. So we have different condition. So definitely we have various grade for the concrete. And then number 2, choice of cement. So here, cement choice varies depending also on usage. So the cement should be tested for performance required by their usage before being tested in the mixed design. And then number 3, choice of aggregate size. Aggregate needed for each mix independent upon the physical properties needed for the design. All aggregate must be quality size before use. So that is why we need to do the sieve analysis in order to be included in the concrete production. And then number 4, type of water. What kinds of water can be used in concrete mix design? So that is why any water used for concrete mix design should be tested before use to ensure that it is within the range of water required for concrete. So here, most all consumable water is good for concrete work but should still be tested. And number 5, water to cement ratio. So here, water to cement ratio can be determined from the concrete mix design, but the ratio of the water to cement should be tested for consistency, initial and final setting, soundness of the cement, workability, slump of the concrete, and compacting factor. And then number 6, workability. So here, this is to measure of the ease of mixing concrete without segregation or bleeding. It mostly depends on the design slump of the concrete. And the last one is about durability. So here, this is the measure of the required strength of any concrete grade at 28 days of curing. And durability should be controlled, tested on site. Next is the objective of the CMD. Why we need to do the concrete mix design? First, objective to provide trial mix design based on the CMD requirement. And number 2, we need to produce a good quality concrete. And number 3, to ensure the most optimum proportion of constituent material to fulfill the requirements of the structure to be built. And number 4, to achieve the desired workability. And number 5, to achieve desired durability on the given condition. And the last one, to produce concrete as economical. Here, the apparatus for concrete mix design is concrete mix design form. So this is the CMD form. Look at here. So we have 5 stages here. So first stages is about the workability leading to the free water cement ratio. So this is the first stage. So here you can see from 1.1 until 1.8. So the objective of this first stage is to determine the free water cement ratio. And then the second stage is about free water content. So here, after we can determine the free water cement ratio, then we can determine the water content here. And the third stage is about cement content. So we can combine the result from stage 1 and stage 2 to determine what is our cement content here. And then the fourth stage is about to determine the total aggregate content. So how to determine the total aggregate content? So we need to get what is the concrete density. And then the last stage, stage number 5, is to determine fine and coarse aggregate content. So from the info at stage 4, we can determine what is the fine and what is the coarse aggregate here. And the last part is to determine what is the actual proportions of the ingredients in the concrete mix in order to be mixing. So here we need to know what is the volume of the specimen, because this volume we multiply with this proportion, because this concrete mix design we design for 1 meter cube. So here another info about the concrete mix design is this column. So here this column show specified. Here specified, and also under stage 1 we have specified, stage 2 also we have 2 specified, and then stage 3 specified for the maximum and minimum content. And then okay, so look at here, under the first stage we have the item specified for the characteristic strength. So specified means that the mix requirement based on the conditions of the project or conditions of the question, conditions of the case study. Okay, that is the specified item. So specified item, everyone need to refer to the conditions of the project and also any info related to the project. And then if here you may see refer to table 1, refer to table 2, refer to figure 1. So everyone need to refer to the related table and figures in order to solve, in order to fit in the concrete mix design form. Now this is the mix requirement for this concrete mix design testing. So number 1, the mix design proportion obtained for 1 meter cube. So that is why if you want to get the actual, you need to get what is the volume of the trial mix. And then number 2, the concrete design strength is given 25 Newton per millimeter square for 28 days with 5% defective. So you must aware with this info, with this mix requirement. Next, application for the pier due to the greater cross-sectional area. So means that this concrete mix design is used for pier concrete. And then for it was assumed a good site control. So this is another condition, the info about the conditions of the site. So here, if we have good site control, so we can choose standard deviation is equal to 5 megapascal. So 5 megapascal is also equal to Newton per millimeter square. And then next, a Portland cement type is used due to its low heat and also economical. And then we have no maximum water cement ratio here. And then also another info, we use a 20 mm uncrushed cost aggregate or choose to do reasonable grade. And then a slump of 60 to 180 mm was specified due to the moderate workability. And then 45% of fine aggregate crush was used based on good fine aggregate grading. So here for this test, you must use your previous grading under sieve analysis test. And then here you need to calculate for 3 cube specimen, means that we're going to prepare the volume of concrete for 3 cube specimen of dimension 150 mm times 150 mm times 150 mm, and also 1 prism beam 100 mm times 100 mm times 500 mm were tested at 28 days. So what is the means of this dimension? So this is the cube test. So the dimension here is 100 millimeter, the height also 100 millimeter, and width here also 100 millimeter. So here you need to times 3 because it requires 3 cube specimen. And also another one, you need to cast the prism beam. So this is the prism beam. So this is 500 mm and here is 100. Now we want to fill in the first stage. So the first stage is selection for water cement ratio. So this is the first stage in the concrete mix design form. So what is the value that we need to specify? So here 1.1 characteristic strength. So specified means that we can get from the mix requirement. So here the characteristic strength is 25 Newton per millimeter square at 28 days. And then here, what is the profession defective? So the profession defective given in the mix requirement is 5%. So you write 5%. And then next, 1.2 is standard deviation. So standard deviation, you may refer to table 1. So this is table 1. Table 1 show standard deviation under different condition. So here we have 3 types of condition. Number 1, good control. Number 2, fair control. Number 3, poor control. And then here is given that if our mix requirement is good control, so we can have 4 to 5. But for the good condition, so we take the highest one. So here we choose 5 Newton per millimeter squared for our testing here. So here standard deviation for our condition, good control at site is 5 Newton per millimeter squared. So now the next part is to get 1.3 is margin. So this margin we need to refer to 1.2. So to get the value of K here, if we have been given the defective means that assume our damage control. So here this is the defective table K. So K factors can be determined based on the 5% defective. For this case is 5%. So 5% means that K is equal to 1.64. So you can write 1.64 here. So this 1.64 we need to multiply for KS, because here we need to determine what is the FM. FM means that target mean strength. So here, so we need to determine what is the target mean strength. So target mean strength is equal to FC plus KS. So FC is given. So FC is 25 here. So this is 25. You may write 25. So KS. K is the standard deviation multiplied with the K. So K is defective here, multiply with the S. S is the standard deviation. For this K, for this case, the KS is 1.64 multiplied with 5. So what is the answer? Here, the answer for the KS is equal to 8.2. Then you can determine the target mean strength FM. So FM is equal to 25 plus 8.2. So it's equal to 33.2 Newton per millimeter squared. Alright. Next, we need to determine what is cement type. So the mix requirement, give the info, we use the OPC. And then what is for the aggregate? So now first is for cost. So for cost, the mix requirement given that uncrushed. So how about the fine? Fine is crushed. So you can refer. if the item specified, you may refer to the mixed requirement, the condition that has been given. Okay. And the next stage is to determine what is the free water cement ratio. So we need to refer to table 2 and figure 1. Next, we need to fill in what is the free water cement ratio. So for this item, we may refer to table 2 and figure 1. So this table 2 given the approximate composite strength of concrete mix made with free water cement ratio of 0.5. So means that here 0.5 if give the datum point at this figure 1. So this figure 1 show the relationship between composite strength and free water cement ratio. So this is the datum 0.5. This is the datum. Okay. Alright. Here, what we need to do with this table 2 and figure 1. So first, look at here. So here, this is the type of cement, first column. Second column is the type of coarse aggregate. And the third column is about the composite strength for the water cement ratio 0.5. So here, what is the type of cement that we use in this testing? So we are using OPC here. And then next column, what is the info about the coarse aggregate? Is it uncrushed or crushed? So we are using uncrushed, right? So what is the strength for the 28 days? So for the 28 days, here, when you map here, so you can get 42. So here, you need to plot 42 goes to the 0.5, this datum line. So here is the composite strength. Okay, the x-axis is the water cement ratio and the y-axis is the composite strength. So now you need to plot this 42. So 42. So this is 40 and let's say this is 45 and this is the 42. So this 42 go to this datum line. So you need to plot the Apsica curve. You need to plot this curve. Okay, why we need to plot this curve? This curve can be determined from the intersection. Okay, the intersection point here. So you try to plot like this. Okay, right. Why? Because we need to determine our water cement ratio. So what is our target mean strength, FM? So our FM, we have calculated that 33.2 just now. So you can plot 33.2. So you get your 33.2. So this is 30. So 33 maybe this is 35. So around this. So from this axis goes to the Apsica curve here. So you go there. And then from the intersections, okay, the intersections of the Apsica, you go down. So you will determine our water cement ratio. So it is about 0.6. So here you meant right here. So yours is 0.6. So here 1.8 maximum. Do we have the info that we have maximum or minimum? We don't have for this testing, right? So you just nail or you just dash. So here, if we have a value, then we need to choose, we need to adopt which is the lower value. So now, if we don't have, you can write. So the water cement ratio is 0.6. Next stage is stage number 2. So stage number 2, we want to determine the free water content. So here, free water content, we need to refer to table 4. So this is the table 4. Table 4, approximate free water content required to give various level of workability. So definitely that water content influence a lot student workability. So now the first column of the table tells about need info about the maximum size aggregate. So here we have 10, 20 and 40. So what is our size that we use? So based on the mix requirement, we are using 20 mm. So what is the type? So second column is about type of aggregate. So here we are using uncrushed, right? So here you can specify your maximum is 20 mm, and then the next column is about info about the slump and VB time. So here we need to specify. Specified means refer to the mix requirement. So here slump test is given range of 60 to 180 mm. So the last column 60 to 180. So the VB time is 0.3 second. So here we can have that. So you go to here. So this is okay. Now, so we have different type of aggregate, right? Because we are using coarse aggregate for uncrushed, and then we are using fine aggregate crushed. So here, this is the column 195 and 225. So here, you may refer to this equation. So to determine the free water content, the formula is equal to 2/3 WF plus 1/3 WC. So WS and WC. WF means that appropriate type for the fine aggregate. So this is for the fine aggregate, means that free water content appropriate to the type of fine. And then here WC means that free water content appropriate to the type of coarse. So you can calculate the free water content is equal to 2/3. So fine is 225 plus 1/3. WC is 195. So you can have that is equal to what? 250. So you may write here 250 kg per meter cube. Next stage is number 3. So here we need to determine what is cement content. So cement content here. So how to determine the cement content? So now we can use the data that we obtain from stage 2 and stage 1. So stage 2, we determine that what? Water content. So what is our water content? Is 250, right? So stage 1, we get water cement ratio. So what is our water cement ratio? 0.6, right? So here is divide. So water content divided by water cement ratio is cement content. So you can determine, you can calculate. So 215 divided by 0.6 is equal to 358 kg per meter cube. So now you need to check. Do we have any specified for the maximum cement content or minimum cement content based on the mix of requirement? If we don't have, you just slash or nil. Slash or nil could be. So here, if we have value, then we need to use that value or modify that value. So this is the condition. Use 3.1 if lower or equal to 3.2, or use 3.3 if more than 3.1. So for this, our testing, we don't have maximum or minimum cement content. So we adopt 358. Next stage is determine the total aggregate content. So now, how to determine the total aggregate content? Here, at stage 4, we need to determine what is the concrete density. So now, if we can determine what is the concrete density, then we can have that concrete density is given weight of cement plus weight of water plus weight of the aggregate. So now we want to determine the aggregate. So definitely that we have density of concrete minus weight of cement minus weight of water. So we can get what is the total aggregate here. So now you may refer to this figure 2. So this is the figure 2. So figure 2, estimate weight density of fully compacted concrete. So here, what is the info that can be used from the previous stage? So now, x-axis refer to the water content. And then y-axis refer to the density. So another value that we need to know is the relative density. So for this case, because of coarse aggregate is uncrushed, so we use 2.6. So here we use 2.6. So this is 2.6. So we need to plot our water content. So what is our water content? Water content is 250, right? So this is 200, 220, so in between. So you need to plot this 250 goes to 2.6 here. So you project this one. You can use ruler. Okay, this intersection, you go to this density because this is one. Okay, you just so let's say what is the value. So maybe we can have that 2340 because it's here 25. So now the density is 2340. So you can have that total aggregate content is equal to 2340 minus cement content is 358, and then minus water content is 250. So you can calculate. So the total aggregate can be calculated 177 kg per meter cube. So don't forget to write here 2340. Now, after we determine the total aggregate content, then we need to distribute what is the amount for the fine aggregate and what is the amount for the coarse aggregate. Next, stage 5. So stage 5 is to determine what is the fine aggregate and coarse aggregate content. So how to determine that? So here 5.1 grading of fine aggregate. So grading of fine aggregate, you can use your own based on your sieve analysis test. So for this example, you can use your own is about 45. That is based on your mix requirement 45%. Okay, now 5.2 refer to figure 3. So this is the figure 3. So this figure 3 is referred to the maximum aggregate size. So here we are using 20 mm. But if you have 10 mm or you have 40 mm, then you need to refer to the respective size of the maximum aggregate. And then now also we need to choose based on these three graphs, number 1, number 2, number 3 and number 4. So based on the slump height. So our test, our slump height is here, the last graph, 60 to 180 millimeter. So now what is others info that we need? So we need to know what is our water cement ratio. So for our test, water cement ratio is equal to 0.6. So now here we need to determine what is the proportion for the fine aggregate. So what is the proportion for this fine aggregate? So now we need to plot. Okay, first we need to plot the projections of 0.6. So this is 0.6. So you just make a line here, 0.6. And then this is the percentage of passing this one, 45. So here 45 is around here. So this is maybe 45. Okay, because in between 40 to 60 we have 50, right? Let's say here. So you need to projection again to these proportions of fine aggregate. So you may use ruler, but now I use my free hand. So the intersection of this. So this maybe around this. Okay, so we just estimate. So now it is about maybe 43. So let's say 43% here. So you can write in 5.2 is 43%. So now we can get what is the proportion for the fine aggregate content. So fine aggregate is 0.43 multiplied with the total aggregate is 177, the total aggregate. So you can get that 0.43 multiply 177, you can have 764, maybe 764.11. So you can have 764. Okay, and then how to determine the cost aggregate content? So definitely we can subtract total aggregate 177 minus 764. So you can get around 1013. Right. So here this 1013 is cost aggregate. Alright. So now you can write here. So now we have calculate for 1 meter cube. So cement content just now is 358 kg. Water is 215, and then fine is 674. Okay, so now based on this cost aggregate, so if we have a maximum 20 mm, definitely we're going to have 10 mm. But what is the ratio? Here, you may refer here. So let's say we have maximum 20 mm. So the ratio of 10 is 1 to 2. So it means that we need to divide by 3 here. 1013 divided by 3. So one part is what? One part is for 10 mm. So you can have around 338. So 338 for 10 mm. So another 2 part is for 20 mm. So it's around 675 maybe. 675. So this is how you can distribute among the size of the aggregate. So let's say if you're testing, you are using the maximum is 40 mm. So if you are getting this cost aggregate, so you need to have this ratio. You need to have the combination of 10 and 20. So this is the ratio 1 to 1.5 and 3. So means that you have 1 plus 1.5 is 2.5 plus 3. So you have 5.55. So you can divide what is the total cost aggregate divided by 5.5. Then you have 1 part for the 10 and 1.5 part for the 20 and 3 part for the 40 mm. So here for the trial make, so what is the volume here? Here is the result of the concrete mix design based on the mix requirement. Right. So now let's say here this is the actual amount for the trial mix. So you need to calculate what is the volume of the specimen. So let's say for our case we need to cast for a 3 cube plus 1 beam, right? 1 prism beam. So let's say you calculate for the volume. So the volume is 0.018 meter cube here. So this is the volume that we want to produce the concrete. So the actual ingredients, so you need to multiply with this ratio 0.018 multiply 358. So the actual one you need to weigh is only 6.4 kg of cement, and you calculate for the rest. So water 215 multiply 0.018 is 3.87. So 3.87 you can around to be 3.9, and then fine aggregate is 3.8, and then for the cost 10 mm 6 kg, and for the 20 mm is 12 kg. Next, what is the discussion that we can conclude here? So here, the relative proportions of the ingredients of concrete have been measured based on the CMD requirement. So we have go through 5 stages, and the last one we can get what is the actual proportions that we can weigh and mixing. And the last one about the conclusion. So here, at the end of this lecture, everyone, students should be able to design the concrete mix design with desired engineering properties. And then the concrete mix design aim is to produce optimal water cement ratio. Later, we will going to test the mix in different tests. For example, workability. So workability, we're going to have slump, VB time, and compaction factor. And then next test is about the hardened concrete. Okay, that's all for today. Thank you.